All right, well, let's get started then. Try and re-wrap our heads around what we've been talking about. We just barely started on Chapter 2. Chapter 2 is focused on the next level of computation. So far, the level of computation we've been talking about is basically what can be done by just finite state machines, DFAs, NFAs, regular expressions, regular grammars. Those were all logically equivalent, and there were languages that they could recognize, and some languages that they couldn't recognize. Our typical example of a language they couldn't recognize was 0 to the n, 1 to the n. And we proved quite a few times that they can't recognize that string. So now we're on the next level of computation here, which is the level of context-free grammars, CFG, context-free grammars. They recognize what we call context-free languages. And so this is our next level of computation. We've already talked about the grammar at this level. The grammar is a context-free grammar, and then we'll also get to today the machine version at this level. So the same way that at this level we have both grammars and machines, at this level we have both logically equivalent versions, grammars and machines, that are able to recognize these languages. Context-free languages are what we call them. So moving on to our next level of computation here with context-free grammars. And just remind you of the exact definition of a context-free grammar, and then we'll do a couple examples really quick to re-wrap our head around it. So what's a context-free grammar? A context-free grammar is a for tuple, so V, sigma, R, S, where V is a finite set of the variables in the grammar. Sigma is a finite set of the terminals in the grammar. Our variables and our terminals cannot have any overlapping symbols. They must be completely distinct. As a general rule, we use capital letters for our variables and lowercase letters or other symbols for our terminals. R is a set of production rules, which is typically what we use to represent our grammar. Rules like A goes to 0, A1, stuff like that. That's what we mean by a rule. So R is a set of production rules. And for a context-free grammar, they have to have a special form. So it's a set of production rules of the form A goes to some string of terminals and variables, like this. So where A is a variable and alpha is a string of terminals or variables. And finally, S here is our start variable. So basically, context-free grammars, the left-hand side of all your rules are just one variable. The right-hand side can be any combination of terminals and variables. That makes it context-free grammar. The variable on the left-hand side is isolated. There's no context to it. It's by itself. So let's write out a couple grammars really quick to remind ourselves of what these grammars are. So a grammar for 0 to the n, 1 to the n, how might we make that grammar? So we'll start with S goes to, what do you think?
You say it could be done?
This could definitely be done with context-free grammar. It could be done with a regular grammar. If we limit ourselves to a regular grammar, then we could do that. This is now context-free grammar. Remember, regular grammars were of the form A goes to, and you could only have a symbol followed by a variable, a terminal followed by a variable. And that was a restriction. And so there was only ever one variable at a time as you generated your string. So now we got context-free, which means we can have A goes to, and then over here we can put anything we want. We're not limited to one variable anymore. And we're not limited to one terminal. We could do 5 terminals and 1 variable, and we're fine. This is a valid production rule for context-free grammar.
Okay, it's kind of coming back.
And we were able to say that a variable goes to this or this. That's right?
Yes, so a variable can have multiple, you can have multiple production rules with the same variable, and we have a shorthand for it. So I can have A goes to 0, I can have A goes to 1, and then our shorthand for that was A goes to 0 or 1. Right.
So we could say S goes to 0, 1 or 0, S1.
0, 1 or 0, S1. Should we include the empty string in here?
Yeah.
Well, then we also want s goes to epsilon, right?
Do we have to? It doesn't feel like it makes so much of a difference in terms of like what it can generate.
If we don't have this rule, how do we generate the empty string?
Well,
Because the empty string is in this language.
oh, that's right. We have to have an empty string.
Right, so we need the empty string. So we need an epsilon there. And so this does, in fact, work. So if we pick any string in this language, we should be able to use this rule over and over again to generate it. So let's pick a string in here. We'll pick the string 0, 0, 0, 1, 1, 1, right? So we start with s always and forever. We can do s goes to 0, s, trying to do my s bigger, 0, s1. So we replace our s with 0, s1. Now we can replace that s again with 0, s1. So that becomes 0, 0, s, 1, 1. Now we can replace that s again with 0, s1. And, well, actually we'll use another rule. We can do s, replace that with 0, 1. And so then that gets us 0, 0, 0, 1, 1, 1. Now we have no more variables in that, so that is considered a generated string. When your string is just terminals, you're done. And so this is a string generated by this grammar.
So, you could just say s could go into s, take away the 0 and 1. Is that
Right, we don't have to have that reduction rule.
Wait, no, you need that one. Oh, no, you're right, you don't.
Yeah, we don't need that.
But
it
you
didn't
could
hurt to have it.
also, if s could go into s and then have the 0 and it would also work too. So, never mind. They both work. Interesting.
Yeah, there's an infinite number of ways that we could write this, but
Yeah, this is all coming back to me.
perfectly valid grammar, and there's an example of generating a string with that grammar. Right? Okay, so let's try one that's a bit tougher. So this time, I want the language, so where x is a binary string with the same number of zeros and ones. So for example, an example of a string in this language is 0, 1, 1, 1, 0, 0. Notice we have the same number of zeros and ones. Okay? Understand the grammar? All right, so let's see if we can think of this one.
Does it have to be random? Or it can be random? Or
We need a grammar that could generate any string in that language.
So maybe we'd have s go to like a0. A would have to go to a 1, so a would go to like 1s.
Perfect. So you got the right idea. So we can think about s is, if we've got an s there, then they have the same number of zeros and ones. We might think about a is we need a 1, and we can think about b is we need a 0. So if we generate a 0, we go to a, meaning we have one more 0 than we have ones. We can also make s go to 1b, meaning we have one more 1 than we have zeros. And then we'll also just do s goes to empty string just to get the empty string. All right, so now A, we could have it go to, if it does a 1, we go back to S. Because S is, we have the same amount of zeros and ones. A is, we needed a 1. We could also have it do 0, and then AA, because now we need 2 ones. Before we needed 1 1, you did another 0, now we need 2 ones to recompensate.
okay.
And B, same idea, 0 goes back to S, we're back to same. If it gets a 1, then we get BB.
Yeah, that makes sense.
All right, so that's usually how you have to think about how to come up with grammars for languages. Usually it's harder to come up with the grammar than, well, I shouldn't say that. Sometimes it's harder to come up with the grammar than it is a machine. And so you think you apply some sort of meaning to each of the variables, what it means to have that variable, and that's how you end up thinking up the grammar, kind of like we just did. So let's try generating the string just to make sure we got it right. So I've got S, what am I going to do first?
Go to 0a.
S can go to 0A. Now what?
0, 1s.
Yep, we can make that a 0, 1S. Now what?
0, 1, 1b.
0, 1, 1B. Now what?
0,
0, 1, 1, 1 dB. Glad we got one of those where it had two variables, so you didn't think you only ever have one. Okay, and now that B, we'll replace this B first. What are we going to replace that B with?
0s.
So that B is a 0s. We get 0, 1, 1, 1, 0s. Let's replace this B at the same time. What are we going to replace this B with?
0s.
Another 0s as well. And then both those s's we're going to replace with empty string, which is going to leave us 0, 1, 1, 1, 0, 0. Perfect. So that's one way we could have done this language. Another kind of natural way we could have thought about this language is we could have thought about it in terms of, again, SAB. If I'm going to have the same number of zeros and ones, that means if I get a 0 somewhere in my string, eventually I need to pair it with a 1. Or if I get a 1 in my string, eventually I need to pair it somewhere with a 0. So we could have S goes to SAB, or the empty string. We could have A goes to 0, S, 1, or the empty string. And we could have B goes to 1, S, 0, or the empty string. So we do an A every time we're saying, I'm going to have a 0 that eventually gets paired with a 1. We think about B as, I'm going to have a 1 that eventually gets paired with a 0. And then S can do as many of those as you want.
Yeah, makes sense.
So using this, let's regenerate our same string. We had 0, 1, 1, 1, 0, 0. Completely, well, trying to show you two different thought processes as you could have had for the exact same language that are kind of different. So let's do this one. So we start out with an S. What are we going to have the S go to?
SAB.
SAB, not a lot of choice there. Which is going to go to
I'm just gonna go with the S 0.
So we want to start with the 0, 1, right? So so we can have this go S0, replacing the A here, replace the A with a 0, S1. So we got our S, A got replaced with 0, S1, and then we still have our B, right? So if we think about that 0, 1 as being that 0, 1, then we need a 1, 0 and a 1, 0 left, right? So
So two B's in the center. Yeah, so it'd be S0, B, B1, B, eventually.
So for that B, we'll replace it with a 1, S0. Maybe you'll be okay with me replacing these S's with epsilons at the same time. Epsilon, epsilon, B is going to be 1, S0. So epsilon, nothing, then we have 0. Epsilon's nothing, then we have a 1. B is going to be a 1, S0. Right? Then we're going to replace that S with the SAB, where the S and the A are going to go to epsilon, and really we just care about the B. So hopefully you're okay with this. 0, 1, 1, B, 0. And then we can replace that B with a 1, S0. So that's 0, 1, 1, 1, S, 0, 0. And then finally replace the S with an epsilon, and we get 0, 1, 1, 1, 0, 0. So one that's a bit harder to work with is we're generating strings, but another way you could have thought about it.
Well, but yeah.
Okay. So throw you back into grammars, give you an example of these were context-free grammars, and we generated that one language that we know for sure isn't a regular language. So for sure it can generate things that regular grammars couldn't. Okay. Now we have a notion of getting a grammar in a particular form called Chomsky normal form. So if we have if these are all our grammars, if these are all our context-free grammars, then a subset of those are going to be the grammars in Chomsky normal form. So A Chomsky normal form grammar is still a context-free grammar. And we just rework it in a particular form. It's kind of like converting an NFA to a DFA. You can convert any context-free grammar to one that's in Chomsky normal form. So Chomsky normal form is just forcing your production rules to follow 3 certain rules. So here it is. A context-free grammar is in Chomsky normal form, provided every rule is of the form, either a variable goes to 2 variables, or a variable goes to just 1 terminal, or your start variable goes to the empty string, where A, B, and C are variables, and B and C are not the start variable. So you can't ever have A goes to and then something start variable. You with me on that? Mm-hmm. So this grammar over here is definitely not in Chomsky normal form for a lot of reasons. One, we have going to S. That's not allowed if you have it in Chomsky normal form. 2, we're going to terminals mixed in strings, not just 1 terminal. 3, that's 3 variables, not just 2. If you have a variable goes to variables, it can only go to 2 variables. Can't ever just go to 1, can't ever just go to terminals. And then finally, we can't have A goes to epsilon or B goes to epsilon. The only thing that's allowed to go to epsilon is a start variable. So those are the restrictions to get it in Chomsky normal form. And the reason that we love Chomsky normal form is because it's a grammar that's really easy to prove things about. So if you have a grammar in Chomsky normal form, it just has some nice behavior. We'll see what that nice behavior is here in a second. But I'm going to give you some intuition for how every context-free language can be generated by context-free grammar in Chomsky normal form. Or in other words, anytime you have a context-free grammar, I can give you an equivalent context-free grammar that's in Chomsky normal form. They generate the same language. That's what we're going to prove. Now, we're not really going to prove this because the proof is just a really wordy version of what we're going to walk through. So I'm just going to walk you through an example with the idea of what the proof would explain you do.
What's the difference between CFL and CFG?
So a CFG is a context-free grammar. A CFL is a context-free language. A context-free grammar generates a context-free language.
Okay.
If you think about it in terms of going back down 1 computation level to regular languages, we had regular grammars. A regular grammar generated a regular language, but you also had a DFA recognized a regular language. So when we talk about all these different models of computation being equivalent, it's because they recognize or generate the same languages. Okay. So, we're going to show that any context-free language can be generated by a context-free grammar in Chomsky normal form. We already know for free, by definition of it being a context-free language, that there exists some context-free grammar that generates it. We're going to show, and furthermore, there exists a context-free grammar that's in Chomsky normal form. How does the proof idea work? We start out with, let A be some context-free language. Then we're given that there must exist some context-free grammar that generates that language. Take that context-free grammar, apply these rules to it, and now the grammar that you're left with is a logically equivalent grammar that's now in Chomsky normal form. That's what the proof walks you through. So I think all that really matters is making sure you understand these 5 rules and seeing an example, and I think you get it. Okay, so what are the rules that we do? The rules are, 1, we add a new start state rule, S naught goes to S. Adding that new rule makes, like, if you had any S's somewhere else in here, now it doesn't matter anymore. So if I add a rule up here, S naught goes to S, now I don't have going to my start variable anywhere over here anymore, because this is my new start variable. I just added it, so none of these could have been going to it. That's the big idea with rule number 1. The idea with rule number 2 is to get rid of all your epsilon transitions.
For rule number 1, I thought you couldn't have a variable going to 1 variable. I thought it had to go to 2 different variables.
You are correct. we'll go through an example and you'll see how all that gets eliminated.
Oh, okay.
These steps have to be done in this particular order.
Okay.
So then step 2 is removing all the epsilon transitions. Not epsilon transitions, sorry. All the generations of the empty string. So that's coming up with a way to get rid of the empty string here, get rid of the empty string here, get rid of the empty string here. If it was possible for the grammar to generate an empty string, then in the process of getting rid of all those, if it was possible to generate an empty string, then you'll have a goes to epsilon rule end up here. And that will be the only goes to epsilon rule from the start.
So you have them go to S naught then.
Yeah, the S naught will end up point to it. I'm not applying the rules yet. I'm just walking you through the intuition of them, and then we'll rigorously apply it to this. Rule number 3 focuses on removing all the rules of a variable goes to a variable. And so that will definitely change whatever was happening here when you added this rule. And so this rule will ultimately get changed. It has to, from how you apply this rule. And then these last 2 rules, they're hard to understand just saying them out loud. Maybe it was a mistake to try and give you intuition for these first without actually walking through an example. Let's just walk through the example.
Okay.
I think that'll do more. So there's a grammar we're going to apply it to. S goes to ASA, whatever. Here's a grammar we're going to apply it to. Let's convert this to Chomsky normal form. Now we'll keep the original grammar there, and we'll write over here. So first we have S naught goes to S as our new rule. And then so far all these other rules are the same, and I'll just keep manipulating it over here. Goes to ASA or AB. We have A goes to B or it goes to S, and we have B goes to little b or it goes to epsilon. Okay, so we just applied the first rule, right? Now the second rule is remove all the epsilon transitions. How do you do this? So first I go down to my B, and I'm getting rid of its epsilon. So starting from the bottom, working our way up. So B can no longer go to epsilon, but I can't change my grammar. That could have gotten rid of some strings. So B no longer goes to epsilon. Now A could go to B, and B used to be able to go to epsilon. So A should still better be able to go to epsilon. So far, notice I haven't changed anything. I know I've still added an epsilon symbol. But since A could go to B, could go to epsilon, then A just being able to skip straight to epsilon doesn't change anything. Furthermore, S used to go to AB, where that B could go to epsilon. So if I add S just goes to little a, we haven't changed anything. So now my grammar should be logically equivalent to what I had before. This grammar should be the exact same as that grammar. Notice B no longer goes to epsilon. We still have it up here, but notice B no longer goes to epsilon. Because we accounted for all the ways that could happen. It used to be B could go to epsilon, so A could have gone to B, went to epsilon, but now A, we just let go straight to epsilon. S could have gone to little ab, and that B could have gone to epsilon, but now we just let little s go straight to what would have happened if we replaced that with epsilon. You with me?
Okay.
Okay,
I feel
so
like it's just kind of like more of a rearrangement, right? Not
we're never actually changing the grammar.
interesting.
The grammar, by the time we're done getting it in Chomsky normal form, this is going to look like a horrendous mess, and it's going to seem completely useless, but Chomsky normal form grammars have a very nice property that makes it easy to prove things about them,
Okay.
even though working with them isn't necessarily nicer. And this one will definitely be a lot easier for us to reason about as human beings than the monstrosity we have here where it's all said and done. So it's not going to get simpler, we're just going to get it in that form. Okay, so B goes to little b. All right, we also had A, so we got rid of the epsilon here. Now we need to get rid of the epsilon transition here. So we had A goes to little epsilon. If we're getting rid of A going to epsilon, then that means S, when it generated ASA, this A could have ultimately gone to epsilon, which would have been the same as it generating SA. This A could have gone to epsilon, which would have been the same as it generating AS, or they both could have gone to epsilon, which would have been the same as it just generating S.
Can you have a variable going to itself?
Yep. Not when it's in Chomsky normal form, but in general, yes. It just is pretty useless.
Right, okay.
Okay, So now we've gotten rid of all our epsilon rules, right? So next, we're going to remove all our rules of the form a variable just goes to a variable. Okay? This one I'll rewrite the grammar now because that's getting kind of messy. So S naught goes to, I can't have it just goes to one variable. Maybe this would be easier from the bottom up. Let's go bottom up.
Okay.
So B goes to little b, that's still perfectly fine. Remember, little b is a terminal. All right, A goes to B, that's no longer allowed. So rather than A goes to B, we do A goes to whatever B could go to, which is little b, right? Now, A also goes to S, which is no longer allowed. Let's come back and fill out. Let's write S. Here's the monstrous. All right. S goes to ASA, that one's still fine. ASA. Or it goes to little ab. Or it goes to little a.
Why is ASA allowed?
Because we just don't allow it from one variable to one variable. This is from one variable to three variables.
Why is the rule set? Well, I'm just gonna.
Yeah, when it's all said and done, what we're left with, we'll follow that definition. But right now, we're doing this. We're removing all rules of the form. One variable goes to one variable. So A goes to S, we gotta get rid of that. S goes to ASA, that one's still fine. Goes to AB, that's still fine. Goes to little a, that's still fine. Goes to SA, that's fine. Goes to AS, that's fine. Goes to S, not allowed. We can just get rid of that one without actually changing it. Okay, going back now, A could go to little b, and A could also go to S. But what does S go to? It goes to ASA, or it goes to little ab, or it goes to little a, or it goes to SA, or it goes to AS. And so now, rather than A going to S, we have A goes to all the things S could have gone to. And similarly for S naught, rather than S naught going to S, we have S naught goes to ASA, or it goes to little ab, or it goes to little a, or it goes to SA, or it goes to AS. And you'll notice that now this variable and this variable are acting identically, but
It's a lot like math formulas, moving stuff around.
so now, this grammar, still completely equivalent to the grammar we started with. We've applied the first three rules. It's a lot messier, but it's still completely equivalent and generates the exact same strings. So next, we apply Rule 4. Rule 4 is to replace all non-isolated terminals with a variable, a new variable, and add the rule that new variable goes to that terminal. So what do we mean by a non-isolated terminal? That's a terminal that shows up not by itself. So this terminal is not isolated, that one is. This terminal is not isolated, that one is. That one's isolated, not isolated, isolated, isolated. So for all non-isolated terminals, we're going to replace them with a new variable, and we're going to add a new production rule for that variable. So now we're going to have S naught goes to. We still have it goes to ASA, that doesn't change. Or it goes to, rather than AB, we're going to add a new variable called use of A, and then B. Is that subscript going to throw you off? Let's do use of 0, and then B, so that we don't think that that's a small terminal with there. So we replace that A with a variable, B. That one's still an isolated terminal, so that one's fine. Then we have SA. Then we have AS. Over here we have S goes to. Same thing, ASA, or U not B, or A, or SA, or AS. We have A goes to little b, ASA, not little ab, U not B, b goes to little b. That's an isolated terminal, we're fine. Now the only one that we replaced was a little a with the u sub naught. So we need to add the production rule, u sub naught goes to a. Right? So still haven't changed anything, still generates the exact same strings. And we're almost there. Finally, in any string with more than 2 variables, we're going to replace pairs of variables with just a new variable, and then add a production rule that that new variable goes to that pair of variables. And we keep doing that until there's only 2 variables left. So if we have a string of 5 variables, we take 2 of them, and we replace it with 1, which leaves us a string of 4, we take 2 of them, replace it with 1, which leaves us a string of 3, take 2 of them, replace it with 1, which leaves us a string of 2. So in this case, we have a string of 3 variables here, and a string of 3 variables here, and here. So I'm going to create a new variable, I'll call this one u sub 1, and I'm going to have it goes to SA, and now I can replace the SA here with the u sub 1, I can replace the SA here with the u sub 1, and I can replace the SA here with the u sub 1. And so now this is our grammar in Chomsky normal form. Completely logically equivalent, and now it's of that form. Every production rule is of the form, either a variable goes to 2 variables, or a variable goes to 1 terminal. And the start variable never shows up on the right-hand side of a rule. And the only epsilon that's allowed is our start string goes to epsilon. In this case, we didn't have it because you couldn't get the epsilon from this. Good? Let's do one more simple version. This time just with our first grammar. We'll do s goes to, let's see, what did you say? You said 0, 1, or 0, s1, or epsilon, right? So this will be much simpler than this one. Let's convert that one to Chomsky normal form, just to see the process one more time, but with something simpler. Make sure we understand it. So first we add a new start variable. So we have s naught goes to s, and we have s goes to 0, 1, or 0, s1, or epsilon, right? Step 2, remove all epsilon transitions. So if we no longer allow s to go to epsilon, s naught could have gone to s, could have gone to epsilon, so now we need s naught goes to epsilon, and that's valid. We can have our start variable goes to epsilon in Chomsky normal form.
Before when we made that grammar on the left, you said we didn't need the s goes to 0, 1 because it didn't make a difference.
Right.
What if you didn't have it here? It feels like it would just carry on. Like if you remove the 0, 1 right there, you wouldn't.
We can remove that, we're still fine. Right now it's not adding anything.
I don't know if you can get the empty string, but how do you get a string that ends? It seems like it would just carry on. If you go to s.
Oh, I see what you're saying. So let's do this a second time. S goes to this time just 0, s1, or it goes to the empty string, right? You're saying, well, if we start with this grammar. So far, our start rule would be the same. So we had s naught goes to s, and then we'd have s goes to 0, s1, or it goes to the empty string, right? Now when we get rid of this empty string, we have 2 possibilities. S naught went to s, went to the empty string, so we need to add the empty string here. Or we can have s goes to 0, s1, where that goes to the empty string, and so we need a 0, 1 here, and so it ends up coming back.
Oh, okay.
Right? So either way we think about it, doesn't matter. We'll just continue with this one using our initial one. Okay. So we got rid of the epsilons. Now we need to remove a variable goes to just one variable. So before we had s naught goes to s. So now we need s naught goes to all the things that s went to, which is 0, 1, or 0, s1. or the empty string still, and then S goes to 0, 1, or 0, S1, right?
Mm-hmm.
Now, we need to remove all non-isolated terminals and replace it with the rule that goes to that terminal. So, non-isolated, 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 non-isolated. All our terminals are non-isolated. So I'm going to add a rule down here. A goes to 0, B goes to 1. And then my 0 here I replace with an A. My 0 here I replace with an A. My 1 here I replace with a B. My 0 here I replace with an A. My 1 here I replace with a B. My 0 here I replace with an A. My 1 here I replace with a B. Right?
I think you missed one. The first one, S naught goes to A0.
AB, right? Okay. So now we removed all non-isolated terminals. Now when you look for strings of variables that have more than 2 variables, take a pair of 2 of them, call it a new variable, plug it in. So finally I'll add C goes to SB, and I'll replace this SB with a C, and I'll replace this SB with a C. And there we go. Now it's in Chomsky normal form. So we can do that for any context-free grammar. We're not going to prove that. You just have to take my word for it. You can read the proof in the book, but it's just a very wordy explanation of walking you through this process.
Makes sense.
Okay.
Why did you make it say? Why did you say like you're like this is the context-free grammar circle, and the Chomsky circle was like inside as
A
if
subset
there
of
was
it?
some context-free grammars that were not inside of the Chomsky.
So a Chomsky normal form grammar and a context-free grammar. For any context-free language, I can have just a context-free grammar that generates that language, or one that's Chomsky normal form that generates that language.
Okay.
That's true. So the languages recognized by context-free grammars and the languages recognized by Chomsky normal form context-free grammars are the exact same languages.
Okay.
But the Chomsky normal form grammars are a subset of just context-free grammars. Every Chomsky normal form grammar is a context-free grammar. Not every context-free grammar is a Chomsky normal form context-free grammar.
But any context-free language
Can be generated by both.
Okay.
It's just like NFAs and DFAs. Every DFA is already an NFA.
Yeah.
An NFA, you got to mess with it to convert it back to a DFA. You can always convert it back to some DFA, but that takes some conversion, some work. So NFAs and DFAs recognize the same language, but DFAs are a subset of NFAs. Every DFA is an NFA, not every NFA is a DFA. You can convert every NFA to an equivalent DFA, but it's not given to you for free that way. That's what I meant. Good point. Yeah, because sometimes we use those diagrams for the languages they can recognize. That's typically how I use those, so I should probably stay away from those circle diagrams when I explain it. Okay. That was a proof I did for that. So now we'll take it for granted that every context-free grammar has an equivalent Chomsky normal form version. And we'll assume that that's proven now. Okay, so now we'll do some theorems here. First theorem we'll do is proving that context-free languages are closed under union. You might remember we did a bunch of proofs like this when we were talking about regular languages. So now we're talking about the closure properties for context-free languages. You remember what it means for it to be closed under an operation?
The language that results in the operation is also a context-free language.
Correct. Does that make sense? She's a lot more used to this terminology than you might be because she's done a lot of stuff with closed.
Yeah,
So let's go back to a simple example. The natural numbers, 0, 1, 2, 3, 4, going up, they are closed under addition. If I take a natural and I add a natural, I get a natural. They are not closed under subtraction. If I take a natural and I subtract a natural, it might be a natural, but it might not.
Okay.
So when we say that a context-free language is closed under union, That means if you take any two context-free languages and you union them together, we're guaranteed it's still a context-free language. So for regular languages, we proved that they were closed under union. We proved that they were closed under intersection. We proved that they were closed under concatenation. We proved that they were closed under a bunch of different properties. Proved that they were closed under star. A lot of them. So we're going to prove that context-free languages are also closed under union. They're also closed under concatenation. They are not closed under intersection. And they are not closed under complement. And we're going to prove each of those things.
Meaning they would go outside of a context-free language?
Meaning if you take the complement of a context-free language, it's not necessarily a context-free language anymore. It could be, but it's not guaranteed.
Yeah, that's what I was saying. It could go outside.
It could be something different.
Okay.
I don't know what you mean by outside.
Would you say, well, that's what I think about when I think outside that scope of what makes something a context-free language. Now, I was thinking you were going to say open, but okay, not closed, fine, same thing, never mind. Thinking of it. Okay.
So let me think of topology for a second. Okay. So let's prove one of these and get an idea for the general proof. They're each very simple proofs. Let me get in front of me just to, well, I'll just write it out. Just don't want to write something that's technically incorrect. This chalk is going to die on me, and there's no more good chalk. This one's good or bad? Shoot. Alright, I guess we'll just have to write with bad chalk.
I don't know if you'd like to tell you this, but I think Taylor hides some at the top.
Hides good chalk at the top?
Yeah, I think he hides it up here. We even actually bought some. We were sick and tired of it. Oh,
Yeah, that's good chalk. You need to get the brand on that chalk and just get a ton.
just text Taylor and find out how I look.
Well, we need to let the office know what brand it
It
is.
was weird. We thought that the crayon brand was really
Crayola?
good. Crayola, yeah. And it was good one time, and then the next time it's horrible. And it's like their batches are sometimes inconsistent.
Yeah. That's crazy how much of a difference it makes.
Yeah.
You wouldn't think so. You had never written on a chalkboard before. What are you being so picky about? It's just chalk.
Oh, it
Right.
drives me nuts.
Yeah, but then when you go and you write with it,
And you
and
can't
you try to erase it. Yeah.
Oh, man.
Okay. Anyways, some theorems. Okay. So first one, we're proving that context-free languages are closed under union. Taking two random context-free languages, unioning them together is still context-free language. That's what we're proving. Okay. So proof CFLs closed under union. Just union. All right. So one. Let A1, comma, A2 be any context-free languages. We don't care. So let A1 and A2 be context-free languages. We're trying to prove that their union is also a context-free language. Right? Now, what does it mean for it to be a context-free language? What's the definition of a context-free language so far?
Is it that it can be generated by context-free grammar?
Perfect. There must exist some context-free grammar that generates it. The same way, going back to a regular language, what was our definition of a regular language?
They could be generated by
Was it a DFA or an LFA?
A language that could be recognized by a DFA. Now, we proved that that was logically equivalent to also being recognized by n of a. We proved that was also logically equivalent to being generated by a regular expression. We proved that was also logically equivalent to being generated by a regular grammar. But the definition that we use in this class for what's a regular language? It's any language that can be recognized by a DFA. That's its definition. What's the definition of a context-free language? It's any language that can be generated by a context-free grammar. So we know what a context-free grammar is. It's right here. That's its exact definition. Any language that can be generated by one of these is by definition a context-free language. So I know that A1 and A2 are context-free languages. And so what do I know about those two?
That each of them can be generated by a context-free grammar.
That each of them has a corresponding context-free grammar that generates them perfectly. So let A1 and A2 be any two context-free languages. Then there exists G1, comma, and G2. We'll actually name these grammars. G1 equal to V1, comma, let's see, it has variables, terminals, production rules, and a start variable. So V1, sigma 1, R1, comma, S1. So there exists G1 equal to that, and G2 equal to V2, sigma 2, R2, and S2. So since those are context-free languages, then there exists these two grammars such that G1 and G2 are context-free grammars, and the language of G1 is equal to A1, and the language of G2 is equal to A2. Right? Long way of saying there exist two grammars that recognize those two languages. We just wanted to name exactly what those grammars were. Because now we're trying to prove that their union is also a context-free language. The only way that I can prove that the union of those two languages is a context-free language is to come up with some context-free grammar that generates this language. So what's the grammar that's going to generate those languages? That's the grammar I need to come up with, right? So we got to create that grammar. So I've got to find my V, my sigma, my R, and my S such that that tuple generates that language. So then we're going to name each of those things. So we'll call V be V1, V2. Sigma equal the union of sigma 1, sigma 2. Comma. And then what are our production rules going to be? How am I going to combine two grammars together with union? What's a high-level strategy for that? Maybe let's just play with this for a second, and maybe you'll see it yourself. So here's the grammar. I'll call it a different letter than S. We'll say A goes to 0, A1, or the empty string. And so this is strings of equal number of zeros, 0 followed by an equal number of 1s, right? And then let's say I do B is, sorry, completely new grammar now. B goes to 1, B 0, or the empty string. So this one is an equal number of zeros, or some number of 1s followed by an equal number of zeros. Now let's say I want to union these two grammars together. How would I do that?
Wouldn't you just like create a new start state, say it goes to A or B?
Perfect. So here's a grammar that generates all the strings of the form like 0, 0, 0, 1, 1, 1. Here's a grammar that generates all the strings of the form like 1, 1, 1, 0, 0, 0. Now I want to come up with a grammar that generates all the strings of the form like this or like this. And the thing is, so here's one grammar, here's the other grammar. To combine these two grammars, we'll union their production rules together, and we'll add a new start variable, S, and we'll say that it goes to A or B. That's it. So let that equal that, comma, and we'll do R, our new production rules, is equal to R1, union R2, union the rule S goes to S1 or S2. So we'll take the rules from the first grammar, union them together with all the rules from the second grammar, and then we'll union it with a new rule, S goes to S1 or S2, where S1 and S2 were the start variables for each of these grammars, right? So then G equal to B, sigma, R, and S is a context-free grammar such that the language of G is equal to A1 union A2. And we're done. We just barely made a context-free grammar that recognizes the union of those two grammars. How do I know it's still context-free? Because all its rules are of the form of that context-free grammar or that context-free grammar or this rule, and this is a context-free rule. So still context-free grammar. So we're guaranteed it's still context-free grammar. It just generates the strings that were in A1 or A2. So there we have it. Not bad, right? All right, now let's say that we wanted to do the concatenation of those strings. So what's the concatenation? That will go off the camera, come back over here. I want something like, so if we were to concatenate these two grammars together, so get rid of that again, think about these as two separate grammars. If I want to concatenate those together, then that means I'm generating strings like, first we have 0, 0, 0, 1, 1, 1, 0 followed by an equal number of ones, and then afterwards we have a 1, 1, 1 followed by an equal number of zeros. We concatenate the two strings together. So here's the grammar for the first part of the string. Here's the grammar for the second part of the string. How do we get the concatenation of those two grammars?
Just add that A goes to B.
Or B goes to A.
Just add that A goes to B.
That could, yeah, just be A goes to B.
If we just add that the start of that goes to the start of that,
No, we can't do that.
then you could end up just generating a string that was in B and not necessarily in A.
Right.
So imagine that we didn't allow these to get the empty string to begin with. So this one has to generate at least a 0, 1. And this one has to generate at least a 1, 0. If I just add to A now B, it's possible for us to get the string just 1, 0. Which is not a concatenation of a string in this context-free language with the string in this. You see? So that doesn't quite work.
Also, you can start generating a string that goes to B in the middle of a string that belongs in A.
Right, maybe A wasn't done terminating yet and you just skip straight along to B.
Would it be A or 0 A 1 B? Wow, never mind. Scratch that.
You're overthinking it. If I write it, you'll say that's obvious.
They're trying to figure out how to get A to stand.
Oh, it's just S goes to AB.
S goes to AB. Now A will generate some string that A could generate, B will generate some string that B could generate. Right.
Yeah, that is.
So when you write all this out, it's almost the exact same thing. We just replace this right here with S goes to S1, concatenated with S2 like that. That's all there is to it.
Yeah, that makes sense.
Right. Obvious once you see it.
Yep.
Okay. Let's do some more playing now. Let's see if we can come up with a grammar for, maybe we can scribble over here, have more space. Let's see if we can come up with a context-free grammar for 0 to the m, 1 to the n, 0 to the n. So some number of zeros, who cares? But once you start generating ones, same number of ones and zeros. You with me? An example of a string that would be in there is 0, 1, 1, 1, 0, 0, 0. Some number of zeros we don't care, but however many ones you have here have to have the same many zeros there. All right. Well, we'll write over here and we'll do the next one over there. Any ideas?
S goes to AB,
S goes to AB.
and then A is just going to 0A and epsilon.
0A or the empty string, perfect. So the A here is just going to generate as many zeros as you want, possibly no zeros. And then the B is going to generate
Just what we had before, so 0 B.
One.
No, it's 1.
Or
It's
the
1
other,
B
no.
0. Wrong order. Or epsilon.
perfect. That's exactly right. Alright, let's try this one. A little bit more tricky. 0 to the n, 1 to the n, 0 to the n. Now we need same number of zeros followed by same number of ones followed by same number of zeros. You understand the difference? Alright, let's try that one. We'll try writing that over here. Maybe start with an S.
Yeah.
Do you know how? Would it be 0, 1, S 0? No, sorry, that's not right.
I think maybe we would start with AB again.
Okay, this is great. It's not possible. Now we'll prove that that's not possible. So that's going to be our telltale example of one that a Turing machine can easily recognize that language, but a context-free grammar couldn't. So the same way that 0 to the n, 1 to the n was our one that it's not regular but it's context-free, 0 to the n, 1 to the n, 0 to the n is going to be our one that's not context-free but a Turing machine can do it.
I see.
Okay? And we'll prove that this one can't be generated by some context-free grammar. It will be a similar type pumping lemma, but we're just going to take for granted, for now, the fact that this one is not a context-free grammar. We're just going to use that for a second. So, kind of need to convince you of the fact it was true without actually proving it yet because you're not ready for the proof. Okay, so we can't do that one. And as you guys were thinking about it, you probably saw the obvious problems with it. It's easy to count two things at the same time, but you can only count things that are right next to each other. You can't skip over and count the next thing over. Anyways, so we'll take that for granted. Now let's prove that context-free languages are not closed under intersection. How can we prove that context-free languages are not closed under intersection?
Find two context-free languages that, when you intersect them, they create a not context-free language.
Perfect. Just find a counterexample.
Right.
Right. So Emma's got the exact right idea. Let's think about one that we know isn't a context-free grammar. Do we know one that's like that? Or sorry, do we know a language that isn't a context-free language?
Like the one we just put out.
Like the one we just did. So that's the reason I introduced it, because that's exactly what we want to do, counterexample.
Okay.
So here's the one that we know is not context-free. Well, I'm telling you it, we'll prove it later. So you know this is not a context-free language. So now we need two languages that are context-free, but if you take their intersection, it gives you something that's not context-free, namely this. So what are those two languages? Give you a hint, we wrote one of them. So 0 to the m, 1 to the n, 0 to the n, intersected with
0 to the n, 1 to the n, 0 to the n.
0 to the n, 1 to the n, 0 to the m is equal to, if we take all the strings that have equal number of 1s and 0s here, and all the strings that have equal number of 0s and 1s here, then you're left with 0 to the n, 1 to the n, 0 to the n, right? You following that? This one right here is a context-free language. We know how to do that. We just did it. This one right here is a context-free language. That would be easy to do. This one right here is not a context-free language.
So, explain to me again how exactly you use intersections work with context-free languages.
Okay.
The logic's a little confusing.
Yeah, maybe we should be a little bit more explicit because I'm just writing that as though it's the set, but let's write it out a bit more precisely. So what exactly are we saying? We're saying we're looking at the set of strings 0 to the m, 1 to the n, 0 to the n, where n and m are natural numbers. So we're talking about that set, and we're intersecting that set with the set 0 to the n, 1 to the n, 0 to the m, where once again, m and n, sorry, that is an m, I know it looks terrible, where m and n are natural numbers. Intersection means and. So we're looking for all the strings that are in this set and this set. So let's pick a random string that seems like it's plausible it could be in both. 0, 0, 1, 1, 1, 0, 0, 0. Is this in both those sets? Well, 0, 0, 1, 1, 1, 0, 0, 0. That's in this set, but it's not in this set. So this is not in the intersection. However, if you put a 0 there, now it is in the intersection. So this string is in both of those sets. So it's in their intersection. And so when you take the intersection of these two sets, you're left with n1 or n0s followed by n1s followed by n0s. It has to be the same count on all three of these in order for the string to be in both these sets. If the string's in this set, the ones have to be the same amount. You have to have the same number of ones as you have zeros here. In order for it to be in this set, you have to have the same number of zeros as you have ones here.
Okay.
And so if those are the same count and those are the same count, then all three are the same count.
Okay.
So we just barely found this is a context-free language, this is a context-free language. You take their intersection and it's no longer a context-free language. It's something different. So since we found one case where intersecting two context-free languages doesn't give you a context-free language, then context-free languages cannot be closed under intersection. The same way that if you wanted to prove that natural numbers were not closed under subtraction, you just need to come up with an example where it doesn't work. And you do something like 7 minus 5. 7 minus 5 gives you -2. -2 is not natural. So you're done. You've proved that the natural numbers are not closed under subtraction. Same concept. Good?
Yep.
Okay. Now, how do we prove that they're not closed under complement?
Also, just find a counterexample.
You can find a counterexample, but this one's even easier. If we remember a special rule that we use in logic all the time. De Morgan's. What does De Morgan say?
What was it? Isn't that the one where you distribute a not over a union or an intersection?
Right. So, A or B, let's try it this way. Not A or B is the same thing as not A and not B, right? So now if you not both sides, then you can think about this as A or B is equal to not A and not B. The point being that you can express or in terms of nots and ands. Now I did this the way I didn't want to do it, so let me switch that. Not A and B is not A or not B was the way I meant to do it. And so A and B is equal to not A or not B. Right? Just switch my ands and my ors. Now when you're talking about sets, ands are the same thing as intersections, ors are the same things as unions, and nots are the same thing as complements. So the set A intersect B is equal to the complement of A union the complement of B. Now, assume that A and B are context-free languages. If context-free languages were closed under complement, then if A and B are context-free, then their complements are still context-free languages, right? If this were true, assume this were true.
Oh, okay, yeah.
Assume this were true and we're getting a contradiction. Quick proof by contradiction.
Okay.
You with me? So assume that's true. So if A and B are context-free languages, then the complement of A and the complement of B are context-free languages. If it were true, which it's not, but if it were, then this now and this would be context-free. We already proved that the union of context-free languages gives you a,
Context-free language.
and then if you take the complement of a context-free language, that would again be
Context-free
a
language.
context-free language. And so you would get that the intersection of two context-free languages is always a context-free language.
That's not the case.
But we just barely proved this is not the case. Context-free languages are not closed under intersection. If they were closed under complement, since we already know that they're closed under union, then they'd have to be closed under intersection. So, if your languages are ever closed over two of those three operations, it's closed under all three. Because you can always express one of them in terms of the other two. And that's what the mortgage gives you. Or we could have thought of a counterexample, but good to remind ourselves of the basic logic that we use for sets.
Right.
Do they both have to be in a complement?
If context-free languages are closed under complement, that means anytime you take the complement of a context-free language, you are guaranteed it's a context-free language. Anytime you add two natural numbers together, you are guaranteed it's a natural number. You don't care what those two natural numbers were.
Right.
So if A and, we're only talking about context-free languages, so if A and B are context-free languages, if they were closed under complement, they're both closed under complement. The complement of both of them would still be context-free. Maybe I
It's
missed
not
your
because
question.
they're intersection. Because it equals the intersection of A and B.
We know that a context-free language intersected with a context-free language is not closed.
And it's equivalent to the complement of a complement of,
So that was the
A.
first thing we proved. We showed that if context-free languages were closed under complement, if they were, then they'd have to be closed under intersection. But they're not closed under intersection. So they can't be closed under complement.
Yeah, I'm just curious. A is under complement and B is under complement.
Right?
And I'm wondering if that is the case where A and B, what about A is under complement, B isn't? Would that be a different scenario?
This is just, what this exactly looks like is kind of irrelevant. The point is, just using unions and complements, I can express an intersection. So the intersection isn't closed. If I can just express an intersection with unions and complements, then both unions and complements can't be closed. Right.
I got that part.
So we knew that that one was closed, so the other one has to not be closed. The fact that it's applying to both these sets is just how it works out in keeping these equivalent. But all that really matters is intersection can be viewed as a function of unions and complements. So if unions and complements are closed, intersection has to be closed. That's all that really matters with drawing out the algebra there. Okay. We did everything there. All right. So now we get to move to the actual machines. Let's see. We'll come like that. Okay, so next section, we're introducing push-down automata. New level of machine. So before we do that, let's go back to our old level of machine, just good old-fashioned NFAs. And this time, draw out the whole machine. Because up till now, we kind of just been talking about the states of the machine, what we call the state control. So here's a machine. it recognizes all the strings that have the substring 0, 0, 1. Right? Straightforward, simple. Up till now, all we've actually bothered drawing is what's called the state control. But that's not all there is to the machine when it's reading a piece of input. There's the actual input tape, which has a current string that it's reading. How does the machine actually work? So we start over here in the start state. The head points to the next symbol that we're going to read. So we read a 1, which gets us to this state. We read a 0, which gets us here. We read a 0, which gets us here. We read a 1, which gets us here. Keep on going, reading the tape. When we finish reading the tape, we check what state we're in. If we're in an accept state, we accept. If we're not in an accept state, we reject. Then we put a new string on the input tape and repeat. Technically, you can think about the input tape as being infinitely long. And once you're done with your input, we have what are known as blank symbols like that. So read the tape. Once you get to a blank symbol, check. If you're in an accept state, you accept that string. If you're not in an accept state, you reject that string. That's drawing out all the pieces of the actual machine. Up till now, we kind of ignored the input tape, right? So now a pushdown automata, a PDA, is a lot like an NFA. It still just has a state control. It still has an input tape that you put your input on. But now we also give it access to a stack. So anytime we read a symbol in transition, anytime we transition from state to state, we have the option of reading an input symbol, just like NFAs did. And on top of that, we also have the option of writing to or reading from the stack, pushing or popping from the stack. Now, I don't know if you have a lot of experience with the stack data structure. No? So, with a stack data structure, the rules are you can only access whatever's on the top of the stack. So, the telltale example, or the typical example is like in a cafeteria where they have a plate dispenser, and it shoves the plates up and you can only grab the plate on top. And once you grab the plate on top, it shoves up and you can only grab the top plate. If you want to reload the stack of plates, you got to shove one on the top at a time and push it down. So you can pop a plate off the stack or you can push a plate onto the stack. So that's basically what this data structure is, except for you get to write a symbol on the plate and then push it on. And then you can, later as you pull out the plates, look at the symbol that you wrote on each of those plates. That's essentially how it works. The only catch is, in a cafeteria, when you run out of plates, it's obvious to you. There's no way for you to ask a stack, hey, are you an empty stack? Did I get all the symbols? And so you'll notice that we always put a $sign here, which is a special symbol that we have, hey, this is the bottom plate. So that's the difference between an NFA and a PDA. A PDA has access to a stack. We can write and read symbols from that stack. Push them on, pop them on. So I always think it's best to just get our hands dirty with an actual example and then go to definition after the fact. So let's write out one of these. So I'm going to draw the PDA for recognizing 0 to the n, 1 to the n. Okay. So here's how this is going to work. Once again, and as always, we just bother writing the actual state control. We don't write these things when we draw the actual machine. Okay. So here we have our start symbol, or our start state, I mean. So I start at some start state. First thing I'm going to do is, without reading a symbol, I'm going to pop nothing off the stack and push a $sign onto the stack. So now, instead of just saying what we're reading, which is how we did our transitions before, you just said this is the input you're reading. We do the input we're reading, which we can read nothing, that's perfectly valid, just like we could with NFAs, comma, what you're taking off the stack, you have the option of taking nothing off the stack, arrow, what you're putting on the stack, pushing on the stack. I often call this what you pop, this what you push. That's just terminology you use with stacks, you just gotta get used to it. But same as taking off, putting on. And so that gets us over to now this state. So if we were thinking about running this machine, let's pick a random input that we'll run it through when it's all said and done. So we'll run it through 0, 0, 1, 1, and we'll draw out the stack as we go to try and help us think about what this machine's doing. That should be enough. So far, going from here to here, all that would have happened is we would have put a dollar sign there. Our head would still be pointing at this symbol. We haven't read anything yet. Good? Now, as I read symbols here, first I don't really want to bother reading zeros. It's implied if you don't add the transition to your PDA, your machine crashes, goes to a reject state. Same thing with an NFA. So PDA is building on NFA. It's completely non-deterministic, same way that an NFA was. Okay, so here, what we're going to do is if we read a 0, let me move these over, so I'm sorry, need more space. 0, 0, 1, 1, we're still on that input symbol. Here's our stack. So far, our stack just has a dollar sign there. Our stack is infinite. We can put as many things on it as we want. But this will be enough space. So if I read a 0, then I don't want to take anything off the stack, but I want to push a 0 onto the stack. So our input, going from here to here, we read nothing. Then we're going to read 0 going from here to here, and we're going to read 0 again going from here to here. So when I read my first 0, my input, the head moves over there, so that now that's the next symbol I'm reading. And I push a 0 onto my stack, so now 0 is the top symbol. I read my second 0, so now our next symbol to read is a 1, and that pushes another 0 on the stack. That's what that state's going to do. It's basically counting how many zeros we've seen. Then we're going to do just an empty transition. Epsilon, epsilon, epsilon. Nothing. We don't read anything, we don't put anything on the stack, we don't take anything off the stack. This state down here, I'm going to start popping off the zeros every time I see a 1. So here, when I see a 1, I'm going to pop the 0, and I'm not going to put anything on the stack. So we read the 0, we read the 0. Now our head's at the 1. Without reading anything, I'm going to move to this state. Now I'm going to read the 1 and pop a 0. So now my head's over here. Now I'm going to read my last 1 and pop a 0. So now we're done reading our input string. With the dollar sign there. Now I come over here to my accept state, reading nothing, popping off the dollar sign, and putting nothing on the stack. So then finally we pop off the dollar sign here. If we pop off the dollar sign, that means we for sure used everything on our stack. So put the dollar sign, put a 0 on every time we see a 0. Then every time we see a 1, pop off the zeros. Only go here if we actually popped off all our 1s. So let's see an example of a string that it would accept to help us see that our machine works correctly. Let's try accepting the string 0, 0, 0, 1, 1 and see how it doesn't accept that. So here, we go to here, on a 0, we put a 0, or we put the dollar sign first, going from here to here. Then from reading our first 0, put the 0 on the stack. Reading our second 0, put the 0 on the stack. Reading our third 0, put the 0 on the stack. Then we come down here, reading our first one takes a 0 off. Reading our second one takes a 0 off. And now we don't have any more input symbols to read. We can only get to here if we can pop a dollar sign off the stack. But there's still this 1 0 on the stack. We don't have a dollar sign to pop off. So we cannot accept this string. There's no way to do it. Remember, it's a non-deterministic machine. So it accepts a string if there's any possible path that allows it to accept. Otherwise, it rejects. We're talking about the non-deterministic version. The same way that we were talking about an NFA up here, not a DFA.
So you don't necessarily, you tell it what to pop off, and if it's not that, then it can't go down that route.
Right, I don't have any transition here for reading the empty string, pop off a 1, or pop off a 0, which is what it needs to do now. It no longer has any more inputs. It still has a 0 on the stack. So I need a transition that's an epsilon while popping a 0. There is no transition like that.
Interesting. I was totally imagining it like you just pop the variable and then use that variable or something. And you didn't actually know what it was, but okay, this is a little different.
Good? Mm-hmm. Maybe let's try one more before we go to our definition. Pretty standard one is WW reversal. Here. Maybe I'll write this one again smaller as like a reference, and then we'll see if you guys can kind of walk me through this next one. So 0 here, we put the $sign on top of the stack. Once we got here, every time we read a 0, we pushed a 0 onto the stack. And then we went down here, doing nothing. Here, every time we read a 1, we popped a 0 off the stack, putting nothing new on the stack. And then we came over here, only if we could pop the $sign off the stack. And this was our except state. Okay, so that was for 0 to the n, 1 to the n. Now let's try a WW. WW reversal. So that strings of the form like, if I do 0, 0, 1, 0, 0, so there's W. Oh, shouldn't pick one like that. Okay. Here's W. Then followed by W reversal would be followed by 0, 1, 0, 0. So you have this string, we want that string repeated, but in backwards order. With me? And we'll use as our test string just 0, 0, 1, 1, 0, 0. For when we get our machine to make sure it's working. Alright, so what should our strategy be?
You're basically going to keep track of everything that you've seen in the stack, and then as you go back down the stack, popping them off.
Right, so as we read the first half of our string, we're going to push it onto the stack. So as I read 0, 0, 1, I'm going to put that on my stack. So my stack will be $0, 0, 0, 1. Then as I read the second half of the string, I'm going to pop off as I see those variables, making sure that it's the same thing I see on the stack.
So that's a way of restriction and enforcing a certain set of...
Forcing matching, yeah. Basically what a stack gives us to do is to count one thing. That's kind of intuitively what it gives us.
I see. Interesting.
I have a question. So can you have, like, I guess we'll figure it out. I'm just trying to see how to make the machine doing this.
Okay, so here's a machine start state. What we're going to do, same thing we did before. We're just going to put a $sign on there for sync. There's nothing special about a $sign. It's just the typical symbol we use for marking the bottom of a stack. Just matter of mention. We can put anything on there to signify we're at the end of the stack. Anyways, then we come over here. So when we're over here, what we want to do is, if I see a 0, I want to put a 0 on the stack, and if I see a 1, I want to put a 1 on the stack. So over here, if I see a 0, I want to push a 0 onto the stack, and if I see a 1, I want to push a 1 on the stack.
You can have 2 arrows going
It's
to itself.
kind of just like a 0, 1 up here.
Oh, that's right.
Right? Remember that now the common thing, just separate. This is what we're reading, this is what the stack's doing. What we're reading, what the stack's doing. So yeah, 0, 1, perfectly fine, loop like that. Then we're going to guess when we're at the middle of the string. Non-deterministically guess when we're at the middle of the string. And do nothing in the middle. And then here, we're going to read off the stack, matching with what we read. So, if I read a 0, I'm going to check the top of the stack better be a 0. And I'm not going to put anything else on the stack. I'm just going to pop off a 0 and make sure that's what it is. If we see a 1, we're going to pop a 1, and we're not going to put anything on the stack. Then, when it's all said and done, the stack better be empty. Otherwise, we didn't get the exact same string 2 times. Otherwise, we probably misguessed where the middle was. So then, we only come here if all that's left on the stack is a $sign, and then finally, here's our except state. Think you got it, or do you want to see a test string run through that?
No, that makes sense.
Good?
Yeah.
Okay. All right. Let's see if we can at least get through the definition of one tonight. Okay, so before we move to the precise definition, let's remind you about some syntax, because remember that these definitions for machines are dense. So I want you to wrap your head around the sets before you wrap your head around the actual definition. So first off, reminder. When you see a set sub epsilon, then that means that set union together with epsilon. So if sigma is a set containing 0, 1, then sigma sub epsilon is a set containing 0, 1, and epsilon. Good? Old notation, we talked about that forever ago, but it's been long enough that you probably forgot. Okay, so now let's do some examples to make sure you understand what these three sets are. So let sigma be the set 0, 1. Let gamma be the set $0, and let q be the set q sub 0, q sub 1. With me so far? So let's write out q cross gamma sub epsilon. What does that look like? So first off, it's going to be a set. It's going to be the set of all the ordered pairs, where the first element comes from this set and the second element comes from this set.
Right.
So it's going to have a
Q and a 0.
q naught and a 0. It's going to have a
Q and a dollar sign.
q naught and a dollar sign. And what else?
Q naught and an epsilon.
Q naught and an epsilon. And then those same things except for using q1. Right? Perfect. Now, the power set of this set. What is the power set? Remember the power set? It's the set of all possible subsets. So it's a set of sets. So it's the set of all the possible subsets of this thing. What's a possible subset of this thing? Well, first off, there's the empty set. The empty set's a subset of that, right? The set that has nothing. The set that has just q naught dollar sign in it. That is a subset of that set. Right?
Oh, okay, so yeah, it's everything where
We could do the set containing q naught epsilon along with q1 dollar sign. This is a subset of this. Right? You remember what it means to be subset?
it's kind of coming back. It's coming back.
Everything in this set is in here.
Right.
So it's a subset. Everything in this set is in here. So it's a subset.
So another one would be those three, for instance.
Another one would be those three, for instance. And another one would be, comma, we could do the whole set itself. Would be in there. Because this whole set is a subset of itself. I don't want to write it out. So
Right.
But yeah, we could have the set containing just those exact three that we had in there.
So it's the whole entire set, and then like minus
It's the
one.
set of all possible subsets.
That's a just ridiculous amount of.
Right. We're not going to write them all out, because how many are there?
I remember. I wish I remember that full simple equation.
2 to the power of however many
Yeah.
are in that original set.
Which is?
Or
6.
To the
Is there
power
6?
of 6.
So it's?
Oh my gosh. It's
4 times 8
64.
64. Yes. I would expect some programmers to know their powers of 2 better.
Okay, my math. My computer does my math for me.
You ever have to like think about your bits?
I'm very conscious of this. No, I really.
I guess
love
you
that.
haven't had to do that yet. Some of our permissions are stored as binary numbers, so you're gonna have to come across that.
Mm.
So like the permission for performing time actions for someone, because we do timekeeping. So the 4 options are: you can perform time actions for yourself, you can perform time actions for people who are lower employees than yourself in terms of their position, people who are the same position as yourself, and people who are a higher position than yourself. And so the position for time events is just a 4-bit number. And if the bit is a 1, then that means they have permission for that particular thing. So since 15 in binary is 1111, that's someone who has permissions for everything.
Mhm.
If you just have permissions for yourself in binary, then we represent that as 0001.
Kind of like Linux permission stuff.
Yeah, a lot of them do that because, well, we were just being overly picky, too concerned about being efficient with our space.
Yeah.
When Linux was first designed, they had to be absurdly clever about how they use every little bit of memory. And yeah, there's a tons of tips and tricks that those early developers had to learn because, yeah, fighting memory was a huge issue. But now we don't really have that problem.
Mhm.
Your app could take a gigabyte of data and nobody cares.
Yeah, I have to be careful not to get too focused on the bits.
Yeah. But yeah, so you do got to know your binary and know how to do bitwise ors, bitwise ands, which is just logic.
Okay.
You just think about ones as trues and zeros as false.
Mhm.
And so a bitwise OR is just ORing all the bits with the top number with the bottom number.
I see.
No, it's a good
Bitwise
advice.
and is and
Reminder that if you're doing the power set, that it's just 2 to the power of.
Yeah, because for each element in the set, when you're creating a subset, you have 2 options. Do I include this element or not? Yes or no, yes or no, yes or no.
This is
You have
probably
6.
the 3rd time that I've forgotten it, so.
Yeah. You gotta practice combinatorial maths, counting. Sounds like a derogatory term, but it's not. You need to learn how to count.
Well, I look forward to class.
Discrete math. Big part of discrete math early on is counting.
Yeah, I forgot I missed that.
I'll be doing it again.
Great. Look forward to
I did that last year. That was calculus and physics.
it. Right. And I ended up taking a massive course, something completely different. I was overloaded.
All right, let's move on to this last one. Make sure we understand it. It should be pretty straightforward now, I think. So Q crossed with sigma sub epsilon crossed with gamma sub epsilon. So this is a set of all 3 tuples now. List of 3 elements where the first element comes from this set, second element comes from this set, third element comes from this set. So this set has 2 options. This set has 3. This set has 3. So total, if we wrote down all the elements, there'd be 2 times 3 times 3.
I thought that would be like where the first element is an ordered pair of the cross section of those first 2 sets, and then the third element is
An ordered pair where the left-hand element is an ordered pair.
yeah.
So that is how you define a 3-tuple.
Oh.
If you went back to like set theoretical definitions, the definition of A, comma, B, comma, C, by definition is A, B, C.
That makes sense. Okay.
So, yeah, we don't really like to think about it that way because the parentheses become unwieldy.
Right.
But anyway, so this has things in it like Q naught, comma, pick something from there, 0, comma, pick something from there, $. Right? And Q naught, 0, 0, etc.
So what's the formula for how many of that would it be?
What's the size of this set?
2.
They're all 2.
Right, so this is a set of 3 element lists, right?
Right.
So everything in there is going to be something, comma, something, comma, something, right? For this first thing, how many options do we have? 2. For the second thing, how many options do we have? 3. Because it's sub epsilon, so the epsilon's included.
Oh, yeah.
So we have 3 options for this one, and for the third one, how many options do we have? So if I have 3 options for that, or 2 options for that, and 3 options for that, and 3 options for that, how many options do I have altogether?
2 times 3 times 3?
Yeah.
Oh, okay.
So there would be 18 possible ways that you could fill that out. Okay, so that's getting familiarized with that notation. So now we'll try and do this definition. And the only hard part is keep in mind these sets. I think. I don't know. I probably shouldn't say that. I don't know what the hard part is. You'll have to tell me. Okay. A PDA is a 6-tuple now. Remember, NFA was a 5-tuple. So a PDA is going to be a 6-tuple now. The added set is going to be the gamma, which is going to be our alphabet for our stack. Because now we don't just need an alphabet for our input, but we also need an alphabet for our stack. Because we can use different symbols here than we have here. Those don't have to use the same symbols. They can, they don't have to. So that's the set that's going to be added, and then our transition function now needs to take into account the fact that not only do we have a state, read a symbol, and go to a state, but we have a state, we read a symbol, and we read something off the stack, and we go to a state and put something on the stack. Right? So maybe, you know what I should have done? I should have written the definition for DFA next to this, or an NFA next to this. That would have helped to see different. Maybe we'll just read it. Maybe you'll get it. Maybe I'm overthinking it. Okay, so a PDA is a 6-tuple. Q, sigma, gamma, delta, Q, not F, where Q, sigma, tau are finite sets, exactly as you expect. And Q is a set of states, nothing different there. Sigma is the input alphabet, nothing different there. Gamma is the stack alphabet, okay, that is different. And now our transition function, delta, it takes as its input the current state you're on, the current input symbol you're reading off the tape, possibly nothing, and the current symbol on top of the stack that you're popping, possibly nothing. Sorry. And it takes you to, and it spits out, a state along with an input symbol to push onto the stack, possibly nothing. Right? Now, since it's non-deterministic, for one input, there's potentially a bunch of places you could go. So that's why we had the power set here. So going back to an NFA, our transition function for an NFA was delta goes from Q crossed sigma sub epsilon, and it goes to the power set of Q. So for just an NFA, the machine we have up here, given a state and an input, so I tell you you're at this state and you read the input 0. Well, there's two possible states you could go to. You could go to this state or this state. So it takes you to the set of all possible sets of states that you could have gotten with that input symbol and that state. Now we're taking as our input the state along with the symbol you're reading, along with the symbol you're popping off the stack. So now your state, the symbol you're reading, the symbol you're popping off the stack, and the possible things that you could put on the stack along with the possible states you could end up in. And since it's non-deterministic, there's many of them. There is a notion of a deterministic pushdown automata. We'll hardly do anything with it, but that would be just getting rid of the power set here. Its transition function would look like that. And so for every particular input, there's one and only one place you could go. Since we're talking about non-determinism, that's why there's that power set there. Very similar to the difference between an NFA and a PDA. An NFA and a DFA. Sorry, I said the wrong things. So the power set there is just capturing the non-determinism. Am I overstressing it? Okay, so that's our transition function. Finally, once again, Q naught is our start state, and F is a subset of Q is our accept states. You can have multiple accept states. So almost identical to the definition of an NFA. The only difference is we got the cross gamma sub epsilon there, and number 3 is the only difference in definition.
So it's a 3-tuple.
It's a 6-tuple.
Sorry, I know. I meant the function here takes a 3-tuple and gives us just a normal order pair.
Almost gives you a set of ordered pairs. Because there's multiple places it could take you, potentially. because it's non-deterministic. Okay, so that's its actual definition. Let's do some more examples with these things, and then we'll talk about the exact definition for what it means for a PDA to accept a string as input. So let's write some more PDAs. Let's see, we already did WW reversal, so we don't need to do that one again. Let's try WW reversal's complement. Now notice, we're not guaranteed that WW reversal's complement is a context-free language. But I'm letting you know, hey, it happens to be. Isn't that nice? So we can actually do this. I'm not tricking you.
Oh, okay.
Okay. So what are all the strings that aren't in WW reversal? How would you describe those strings?
Isn't it that machine that we made, except you switch the accepts states? You can do the...
That works for a DFA. When it's deterministic, you can just toggle the accept states to non-accept states and the non-accept states to accept states, and that works.
Okay. Doesn't work with the PDA though?
It doesn't work with an NFA. Because, how can I best give intuition for this? An NFA accepts if any possible path cause it to accept. There were still a bunch of paths that the string could have taken with an NFA that were reading the string and it rejected. It was just if there was a path.
Yeah.
And so toggling that, you might now,
Accept some of the same strings.
right, you could accept some of the same strings and you could not accept some of you toggle an NFA, you're probably close to accepting everything. Because imagine we toggle this in. Notice now that becomes an accept state. Now it accepts every string.
Right.
Right. So, yeah. Can't just switch the start states in to accept states and accept to start. That doesn't work. If that did work, then it'd be closed under closure. Okay, so how would you actually describe these strings? Like if you tried to give a verbal description of what these strings are, how would you describe them?
Strings that aren't symmetrical.
Strings that aren't symmetrical. Is this a symmetrical string?
Yeah.
So should this accept this? Is this in this language?
Oh. It is in that language.
But it's symmetrical.
Right.
So how would you describe these strings? You don't necessarily need to get it in one go. Say it's this and this and this if you need to. Or this or this or this. Usually helps to think of like bite-sized chunks of strings that you can just capture. Can you think of an easy way of describing some subset of strings that's in here for sure?
I'm actually not very caught up. Remind me what the W represents and the R represents.
Okay, so the W represents any string we'll think about in terms of zeros and ones.
Okay.
And then WR represents that exact same string except for in reverse order. And now they're concatenated together. So W or 0, 0, 0, 1, 1, then W reversal would be 1, 1, 0, 0, 0. Concatenate those two together, and that would be in that language. Or sorry, that would be in this language. We're talking about the complement. So this is not in there.
So it's going to be all odd number strings and then all even number strings that aren't symmetrical?
That is a great way to think about it. So definitely if the string has odd length, it's in here. If the string has odd length, it's definitely not in here. Furthermore, if a character in this string mismatches a character in this string, then it's not in here. And it turns out that's probably the easiest way to think about this. So we start out with our start state. And we'll do the odd strings first, since those are the easiest to think about, right?
Okay.
So we'll non-deterministically guess that we're looking at an odd string. And we'll do nothing. Going up to, this is checking it's odd. Now, call this an accept state. Sorry, that's terrible. Now for any input symbol, sometimes we use sigma to signify, I don't care if it's a 0 or a 1 or whatever. For any input symbol, we're going to push nothing, pop nothing. We're completely ignoring the stack. Then we go over here. And for any input symbol, completely ignore the stack, we go over here. So we jump up here, odd, even, odd, even, odd, even. If it turns out it's odd, it'll be accepted. And obviously we don't need the stack to recognize odd length strings. That's easy to do. So this part of the machine will recognize it if it's odd length. Now we'll create the part of the machine that recognizes it if it's even length and has a mismatch somewhere. Right? Okay. So how are we going to do that? Our strategy is going to be, as we read W, push it onto our stack. And as we read this W, pop it off of our stack, matching it, and make sure a mismatch occurs somewhere.
Okay.
Then after the mismatch does occur, make sure that the amount we popped is the same amount that we pushed. And so we didn't just do a mismatch somewhere early in the string. You see what I'm saying? Maybe writing it out will be more clear than trying to say it all in one go. So first we'll come down to this part. Now since down here we actually care about our stack, then we're going to do our epsilon, oops. I'll just write straight like this. We're going to actually push a dollar sign onto the stack to get us started. Okay? So that's as we get to this state. In this state, we just push on whatever we see. So if we get a 0, then we're going to push a 0 onto the stack. If we get a 1, then we're going to push a 1 onto the stack. Okay. Now we're going to non-deterministically guess that we're at the middle. And now we're going to W reversal. So when we're at the middle, we're just going to guess we're at the middle, somewhere along the way. And now, over here, it's okay if some strings match. We just need there to be at least one mismatch. So if some match, we're still perfectly fine. We don't need to crash. So it's okay if we do 0, pop off a 0, push nothing onto the stack. And if we see a 1, it's okay if we pop off a 1 and push nothing on the stack. But somewhere along the way, we need a mismatch. So to go to our next state, we either need to have seen a 0 when we popped a 1 off of the stack, or we need to have read a 1 when we popped a 0 off of the stack to get to our next state. And now once we get here, we for sure seen a mismatch in our string, right? Now the last thing that we need to be careful of is making sure that we guess the middle at the correct spot. So from here on out, for every input symbol, we need to pop something off the stack and make sure that our input finishes exactly when our stack is empty. No sooner. You with me? So for here, for whatever our input symbol is, we don't care. We're going to just pop whatever's on the stack, we don't care, and we're going to push nothing onto the stack. Anything, sorry, that's a gamma. We don't care, anything, epsilon. Then, finally, if by the time we're done with input, our stack is also empty, we can accept. So, when we're out of input, we can pop a stack or a dollar sign off the stack, then we can accept. All right, so let's walk through a concrete example with this, and that'll probably help see the logic of how it all works.
Yeah, so I can point at it. The 1 comma 1 is popped off and the 1, 0 popped off, that's the very last read, essentially, that we want, where we want to do that.
This one?
Yeah.
Well, this one, now I don't care what I read, and I don't care what's on the stack. Just read it and pop off whatever's on the stack. So I'm making sure every time we read an input symbol, there's still something on the stack. Because now we don't care if they match or don't match. If they match, we don't care. If they mismatch, we don't care. We just care that there was at least one mismatch. Right?
Okay.
So now from here, all I care about is for every input symbol, there is something on the stack. Because if our stack runs out while I'm still reading input symbols, then that means I guess my middle wrong.
Okay.
Or if I still have things on my stack, when I run out of input, that means I guess my middle wrong.
Right.
So let's do an example to see how this rejects a string like 110011. It should not be able to accept that string.
Okay, yeah.
Right? So obviously it won't accept the string up this way. Let's see why it won't accept the string this way. You with me? So I'm going to try it over here, 110011, and we'll draw a picture of our stack here. Here's draw down for some reason. Right. Okay. So we come down here, here's our input. I'll just put a line under what we're reading. We're reading a 1. So at this state, we're reading a 1. So we read that 1, and we push a 1 on the stack. Sorry, we already got a dollar sign on there. Going from here to here, dollar sign. Read a 1, put a 1 on the stack. And we read another 1, and put a 1 on the stack. So now we read that 1, put a 1 on the stack. And now we might guess, okay, now I'm going to guess that this is the middle, and switch over. So I'm going to get my mismatch. So going from here to here without reading my 0, now I come over here. Here, I read a 0, but is there a 0 on my stack? No, there's a 1. So that's this one, 0, 1, going to here. So I read that 0, so now we're reading the symbol, and I pop a 1 off the stack. Now this says, read a symbol and pop something off the stack. I don't care what they are. So now it reads the 0 and goes to 1, and it pops a 1 off the stack. Now it reads that 1, going to here, and it pops the dollar sign off the stack. Now it reads that 1, and there's nothing to pop off the stack, so it crashes and rejects. You see how this part is important to making sure that the count is the same at the end? Now let's do it with the string that it would accept, and maybe that will also help clear it up. So here's a string that it would accept. We could do 1, 0, 1, 1, 1, 1. Notice that those have a mismatching character right there. So this one, reading through, going from here to here, we put our dollar sign on the stack. There's our dollar sign. Now we're in here. As we read 1, 0, 1, we're going to put 1, 0, 1 on the stack. So we read that, so our head is reading this symbol now. This is our next symbol. And we just read 3 symbols, and so now we go to here doing nothing. And we're non-deterministically guessing that we've read half our string, which is correct. Okay, so now, right here, we say, you can read a 0, pop a 0, or read a 1, pop a 1. We're going to read a 1 and pop a 1. Right? Which leaves us here again. So we take that loop. So now we're reading this one, and we took a 1 off of the stack. Now we're reading a 1, but there's a 0 on top of the stack. So we can't take this loop again. We have to take this loop. We're doing this transition. We're reading a 1 and we're popping a 0. So going from here to here, we read that 1, so now we're reading our last 1, and we popped a 0. Now this one says, I don't care what the input is, I don't care what's on the stack, read an input, pop the stack. So it reads an input, so now we're done reading our input, it pops the stack.
I see now. It's all coming back.
Right, so now it's just saying, make sure that the amount of input we had left to read was the same as the amount of stack we had left to read.
Right.
And now this says, read nothing, and your stack better just have the dollar sign on, pop the dollar sign. So now we're here. Stack's empty, we're done with our input. Are we going to accept it? Yes, and we accept.
That makes sense.
Yeah. It's a lot of notation, but it's really not that complicated once you get used to it. Just looks messy. Okay. Contour. Should we do the next two, or should we call it? Let's do the next one, and then we'll save this one for next time. That's what we'll do. All right. So let's see if we have any ideas for how to do WW. Now we'll worry about that later. WW. So we got to read one string and then follow it by the exact same string again. So as we read this string, we just push it onto the stack, and then as we read this string, we just pop it off the stack, checking them, right?
Right.
Well, no, that's how we did WW reversal. Because remember, as I read, so picking a string out of here, so an example of a string in here would be the string like 0, 0, 1, 1, followed by 0, 0, 1, 1.
Right. Okay.
So as I read this part of the string, my stack is going to look like $0, 0, 0, 1, 1. So now when I'm reading that 0, how do I make sure that it matches that 0?
I don't know if this is the case for like all strings, but our stack is basically the string that's following, except all the ones are zeros and all the zeros are ones.
That's a coincidence of our string. If
Yeah.
this started in 1, then this would have been a 1, 0, 0, 1, 1. So then we would have had a 1 there.
Oh, that's right. Okay.
Dollar sign.
And you can't.
So when we get to that one, we need to check it against the bottom of the stack.
You can't unshift right here then.
Right? How do you get to the bottom of the stack? The only way we can do that is to get everything off the top first. Then as we get everything off of the top, how do we remember what those top things were?
Is this a trick question then? Or?
Well, we could have a state that remembers, hey, we saw 1, and then another state that says, hey, we saw 1, 1, and another state that says, hey, we saw 1, 1, and then 0. And another state that says, hey, we saw 1, 1, 0, 0, and all the way back to this 1. But we could potentially have infinitely many things on top of there. And a state machine only has a finite number of states. You don't get infinite states.
So is this not doable?
So it's not doable, and trying to make sure you got the intuition for why it's not.
Right.
So can't do this one. Impossible. With a finite state machine. Turing machine, real easy. So this is another typical example of one that can't be done with context-free grammar, but can be done with a Turing machine.
Could you do it with 2 stacks? I mean, I know that's like outside the definition of a PDA, but
Yes, you can. With
Or
2
you can
stacks.
do shifts.
So
Unshift.
crazy thing. Take a PDA and give it 1 more stack. You now have a Turing machine.
Really?
Yes. So you have just an NFA, and all it can do is regular languages. You give it 1 stack, and now you have a PDA. And now it can do everything a context-free grammar can do. You give it 1 more stack, and now you have a Turing machine,
You can do anything.
which can do everything Turing machines can do. You give it another stack, and it can still only do what Turing machines can do. And you give it 10 billion stacks, and it still can only do what a Turing machine can do. So got a finite state machine, that's your first level. Give it 1 stack, context-free grammars. Give it 2 stacks, Turing machines. We don't know how to make it more powerful than that.
Is that the highest level Turing machine?
Yeah, we don't know how to build a model of computation higher than what a Turing machine can do. And so, by definition, an algorithm, we haven't gone to that yet, that's the church term thesis, but by definition, an algorithm is what a Turing machine can do. What's computable, what Turing machines can do. And so it's by definition the highest level of computation, because computation is one.
What a Turing machine can't do, so I'm looking for it.
Have we not already talked about the halting problem? Just to like help me see ahead? We didn't?
I remember you talking about that. I can't remember.
All right. So, yeah, so we'll put a pin in it now. So WW complement, even though it's a complement of one that can't be done by context-free language, it turns out this one can be. So we'll pick it up next time with that one as our example to delve us into all this. And so that's the end of the lecture, and we'll just talk about halting problem real quick to give you intuition for what a Turing machine can't do. The halting problem, intuitively,
Oh,
is
it's not knowing when to quit or stop. It's a loop, endless loop or something.
don't really have a lot of space.
Like a call stack or.
Can't make a mess of it. We'll end the lecture right here because I can show you a quick video that goes over it faster than explaining it, and we'll cover it in the class eventually.